Right. Let's now look at rotational equilibrium. One of the first things that we know is that if you have a moment, it produces a turning effect. So an object that's in rotational equilibrium, the net moment about any point is zero. Right? How do we then define a moment? Right? We have used the word moment in the first line over there, and moment again. So how do we define moment? The moment about an axis is the product of the force and the perpendicular distance from the line of action of the force to the axis or point of pivot. This is given in the equation where the moment tau, this is the Greek letter tau, is equals to force times distance, perpendicular distance. So let's look at it, right, in a bit more detail. When the force and the line of action, right, when the perpendicular distance to the force, right, is perpendicular to each other, right, the moment value is very easy to calculate. Just take the moment, it's just the value of the force F multiplied by D, right? And once again, it seems that the alphabets have decided to disappear from my laptop and it's back again. Right, so you just take the value of this F, let's say this F is a value of 10, and this 1 meters, then the moment is just 10 times 1, 10 Newton meters. Okay? The situation is a bit more complicated when the force is no longer perpendicular to, right, the rod itself, right? The force is acting not perpendicular to the rod. We then have to find the perpendicular distance of the force to the point of pivot. So if you look here, the usual way is to take the force, draw a line of action, that is a dotted line. Something is wrong. Not sure why that is happening. But it doesn't allow me to draw onto the diagram directly. But you can see here where my mouse is, right? That the force, if you draw the line, actually it goes along this line, right? And the perpendicular distance is the distance from the pivot here to the force. So if the rod is r, distance of r, the perpendicular distance is r sine theta. In case you are not sure how we got that, well, sine theta, it's the perpendicular distance, right? This is not working. For some reason, this is not working. Is equals to the perpendicular distance, which means that the perpendicular distance is r sine theta. Okay, and hence the moment is simply the force times r sine theta, which is the perpendicular distance. Okay. Next, there are a few intricacies over here. Sometimes when you turn something, you exert not one force but two. Right? If you were to spin a basketball with two hands, one going towards you and the other hand pushing outwards, right? That is essentially, it could be a couple, right? When you try to spin a basketball in place, right? So this is a couple, has a definition. It's a pair of forces of equal and oppositely directed parallel forces whose lines of action do not coincide. Lines of action do not coincide. Okay. If you look at this diagram here, this force F and this force F, they form a couple. And for a couple, there's a special name for the moment produced. It's called a torque. T-O-R-Q-E. The torque is a turning effect due to a couple, right? Given by the product of one of the forces and the perpendicular distance between the couple, right? So again, you just take one of the forces multiplied by perpendicular distance, you get the turning effect. Let's look at some examples to further our understanding of moments and rotational equilibrium. So during gym class, two students were made to apply a force of 10 newtons in opposite directions on the opposite ends of a gym ball, so the gym ball will spin in place. Spinning in place means that the center of mass does not move. The diameter of the gym ball is 1 meter, that's pretty big. Right? Calculate the resultant torque. So let's add in the required values, right? Which is again strangely missing at its back. Right? So for some reason, when I click on the button, it comes back. Right. So let's look at the diagram here. We have a force of 10 newton and force of 10. This is a couple. The perpendicular distance between them is 1. If we look at the equation above, the diagram example above, the moment is simply tau equals to one of the forces multiplied by perpendicular distance. This is just 10 times 1, 10 newton meter. Okay. So what will happen to the basketball, or rather the gym ball? It will start to spin in place. Is that rotational equilibrium? That is not. Let's now look at the next example. Right? You have a pulley subjected to these forces. Calculate the value of the moment tau required to keep the pulley in rotational equilibrium. So let's take moments about the center of the example. Right? Taking moments about center, right, you should write that down. Taking moments about center. You must, for it to be in rotational equilibrium, we say that the clockwise moments must be equal to the anti-clockwise moments, right? And if you look at this, what do we have? We have clockwise moments 10 times 0.5 meters. It must be equal to 5 times 0.5 meters. And there is a turning moment tau given. If we rearrange and we solve, we get tau equals to 10 minus 5 times 0.5. Essentially, the answer is 2.5 Newton meter. Right? That you need to apply a turning moment on the gym ball of 2.5 Newton meter to prevent the ball from spinning. Next, we use a pulley. In this case, it's a massive pulley of 1 meter. Same thing. Right, calculate the value of the force to keep the pulley in rotational equilibrium. So this force is applied at the top of the pulley, perpendicular to the radius. Right. So once again, let's take moments about the center. Right, let's so take moments about the center. What do we have? Well, we could actually do the same calculations as we have done above, but we know by looking at these two examples, right? If you look at these two examples, that they are actually the same situation, which means that the force you are applying multiplied by the radius must give you the turning effect or the moment they've calculated in the previous question, which is 2.5 Newton meter, right? Because this value here must be this value because it's the same situation. Just that in the previous case, you do not know where the force was applied. So once you know this, it's very easy. Force must be 2.5 divided by 0.5. So it is 5.0. Alright, let's now look at another diagram, last one. The force F now is tilted at an angle, no longer perpendicular to the radius. What do you think is the value of the force? Would it be larger? Would it be smaller? Well, the answer would be that it should be larger. Why is this so? Well, let's take a look. Now, if we zoom into the diagram, we can see that the line of action of the force, the perpendicular distance has been reduced. Right, the perpendicular distance is no longer the radius, it's a distance that is shorter than the radius. What this means that the value of the force F must be increased to provide the same moment. Okay, so let's see how this pans out. Let's take a look. This is also the angle. So first, let's try to find the angle or the perpendicular distance D. Right? Here, let the perpendicular distance D be D, right? Alphabet D. So if you take cosine theta of this triangle here, we have perpendicular distance D over the radius R, right? The perpendicular distance D is then R cosine theta, which in this case is 20 degrees. We sub in the values, we should get the value of 0.47 meters. That's the perpendicular distance. To provide the same moment of 2.5, right? Let's use the equation. Moment must be force and perpendicular distance. The same moment of 2.5 is required. Force is the value you need to find now. The distance is 0.47. We can rearrange and find that the value of F is essentially 5.32. 5.32. The value of force has increased. Right? Value of force has increased.